Okay, so today we're going to discuss the definition of integration. Now, actually, integration is only defined for sorry, for definite integration. Indefinite integration, or the antiderivative, doesn't actually have uh, you know a definition, except maybe for antiderivative, but like an actual solid definition doesn't exist uh, for the antiderivative. But we do have one for definite integration. It's actually quite interesting to think about or to explore. Okay, so we have if we have the integral from a to b of f of x dx is defined as the limit as n goes to infinity of sigma I equal 1 up to n of f of xi times delta x, where delta x equal to b minus a over n, and xi equal to a plus I delta x. And this may look terrifying, but it's, once you understand it, it makes a lot of things easier. Like, it makes your life much, much easier. So, what are we doing here? Uh, let's say for some n, where n is an integer, okay, a positive integer, okay. For some n, we need to see what this does, okay. So, if you have a function, some function f of x, okay, that looks like this maybe, okay, and you're trying to find the area between x equal a and x equal b. What this says is that you separate it into n parts, each part having a width of delta x, where delta x is b minus a over n. So you divide it into n parts, so the width of one of these rectangles is b minus a over n, okay, and you take the value at this at, like, let's say this is x0, this x0, this x1, this x2, and so on. So you separate it into n parts, and you have x1, x2, x3, x4 up to n, and you take the value at at 1x, and you multiply it times delta x. You take the value at some x, and you multiply it by delta x, and so on. So you're approximating the area, but as you let n get bigger and bigger, you get closer and closer to the area. And well, this might seem okay. I may already know this, okay, but what's actually fun, or what's actually useful from this, is that it doesn't just work for area. It's integration is a sum of products before it's a way of calculating area. Okay, so let's see that. If I have a body that's moving at some changing speed, okay, that's not a constant, okay, I want to know how much distance this travels in a certain amount of time, okay. How much distance does it travel, okay. If I try to find it, what I'll actually end up doing is that I'll say, okay, you know what? I don't know my speed at every time. So what I'm gonna actually do is I'm gonna separate it into smaller time segments, and just say, for this time segment, the speed is approximately some value of v. Okay, and then take that v multiplied by the time for that specific, like for that segment of time, and keep adding that up. Okay, so you're adding v times delta t over time. So what you're actually doing is you're integrating. Okay, you're taking your value of v at this specific position, you let the time move a little bit of time, of you call it delta t, and you multiply them, you find that small distance, and you keep adding that up. Okay, so it's the process of adding up products, and this is very useful. For example, if you have a block that you exert some force on, and you move it a certain distance, but that force isn't constant. It's a variable force. Okay, what do you do in this case? You separate the distance into very, very smaller, tiny segments. You say, okay, for this segment, the force is approximately some value of F that you chose. Okay, you take this value of F, you multiply it by the small distance that you moved, and you keep adding that up. Okay, as you go. For example, if you have, uh, I'm sorry, if you have like a ring of charge, okay, and that ring of charge has some charge distribution along it, what you actually do, if you want to find like the resultant force at some point here, usually the resultant force is the sum of all forces acting on that object. So you separate this ring of charge, you split it into very tiny segments. Okay, you calculate the force between that segment and your charge. Okay, and you keep adding that up. Again, you're integrating. The essence of integration is not area. Now, every sum of product could represent some area, but whether that is useful or not isn't certain. Okay, for example, here you keep adding up the force times distance. You take your block, you let it move a small distance, and you say, okay, for that small distance, my force was some value of F. Okay, you keep on adding F times S, Fi times delta S. Okay, is it beneficial to know that this is the area under the force displacement graph? It's not useful. It's a fact, but it's not a useful fact. So the essence of integration is not area. You're adding up products. Okay, for example, let's say this is the path of a certain particle as it moved along the xy plane. Okay, if I want to calculate the distance that this particle moved, what should I do? Well, I can't calculate the length of this weird ass shape, but I can calculate the length of uh, of a line. So what I do is I come here, take a small segment of this line, let me call it DL. Okay, this is dx, this is dy, and since dy is normal to dx, you can say that dl equal to dl squared equal to dx squared plus dy squared. Okay, okay. How is that useful? Well, square root both sides, you get dl equal to square root of dx squared plus dy squared. Well, I can't integrate with respect to two variables. It's ludicrous. Okay, but if I say dl and I pull out the dx, it's gonna be square root of 1 plus dy over dx squared multiplied by dx. Okay, and now you can integrate. You can add up your L and your X. Sorry, you can add up your DL and you get your L equal to this. Okay, so you could calculate the length of a curve. Okay, the opportunities are endless, and you're taught two things about integration once you're introduced to the subject. It's A1, it calculates the area. 2, it's the antiderivative. It's the opposite thing to integration. Yes, to differentiation. Okay, so let's see what integration does to a derivative. You have your derivative at some value of your graph, okay, and you try and you let's say you want to integrate it. Okay, your derivative is the gradient of this tangent, okay, which is this is dx, this is dy, so it's dy over dx. Sorry, it's dy divided by dx. Okay, so this is the gradient of this tangent. Okay, so let's try to integrate that with respect to dx. So let's do our usual thing. Take from a to b, some value of x that we call a to some another value that we call b. Okay, and we separate this part into very tiny segments. Okay, take your derivative, which is dy over dx. Okay, or for non-infinitesimal values of x and y, it's delta y over delta x, the change in y over the change in x. Okay, and you take that as delta x goes to 0. Okay, so we call it dy over dx, and you take that and you multiply it by your delta x. Okay, and you keep on adding that up. Okay, so you're adding up the small dy's, you're adding up this plus this, you're adding up this and this and this, you're adding up all these values of small, infinitesimally small changes in y. So what you get is a big change in y. Okay, so it's your final y minus your initial y. Okay, which this might look like your fundamental theorem of calculus. It says that the integral from a to b of f of x times dx is equal to f of b minus f of a. Okay, so it's your f of b minus f of a, where f is the antiderivative of x. And you can see how this is the opposite process to differentiation. Instead of taking the change in y and the change of x and dividing them, you're multiplying by the change of x and you're adding the change in y, so you get the y. You're adding the very small changes in y, so you get your change in y. That's your fundamental theorem of calculus here. Yeah, I don't know what happened. So this, I hope, should help you identify any problems that you can solve with integration, and yeah, I think that's about it. I'm gonna end the video here. Thanks for watching. Yeah.